So in this slide we talk about quasi-affine algebraic sets. So these quasi-affine algebraic sets are nothing but another name for open sets. We have already described open sets in the previous lectures. So let us write what I have just said. So quasi-affine algebraic set over K, where K is closed, is nothing but an open subset U. Yeah, this open subset U is subset of some closed set X. Yeah, so X is closed, which is subset of AN, and U is an open subset of X. So let us describe this pictorially. First I draw X. So X is nothing but a parabola. It's a closed set defined by our equation. Now I take 2 points out of it. We have taken 2 finite points out of it. What we get is an open subset, and this open subset we call U, and this is precisely what we are also calling as quasi-affine algebraic set. It is also, such a set is also called locally closed. So we have 3 names now: locally closed, open sets, and quasi-affine algebraic sets. So now let us describe the morphism between two quasi-affine sets. So let us first write two quasi-affine sets or open sets. We choose V and U. So precisely like we described morphism between closed sets, we define morphism between open sets. So we have a morphism phi, and this consists of tuple of regular functions, phi 1, phi 2, phi 3, all the way to phi m, because dimension of V is am. So all the way to phi m. Now each phi I is a regular function. Now notice that for closed sets we had each phi I was a polynomial. Here we have phi I as a regular function. That means it is a form of a fraction, f over g. Yeah, again if V and U are closed, this regular function becomes a polynomial. That is because of the theorem we covered in the previous lectures. So yeah, if U and V are closed, this will phi I, which is a regular function, will just become a polynomial. So important is that you compare this with what we have already talked about, morphism of closed sets. So again, regular function is of the form f over g, and on closed sets it becomes a polynomial. Another important point is that these morphisms make these quasi-affine algebraic sets over K into a category. So they make the quasi-affine algebraic sets over K into a category. Now let us talk about some examples. So before we talk about examples, I just want to talk about what would be an isomorphism. So isomorphism of quasi-affine sets, quasi-affine algebraic sets. So now take two quasi-affine algebraic sets, X and V, and we have morphisms between them, var phi and phi. So this is var phi, say, and in the opposite direction it is phi. So these two sets, X and V, are isomorphic if we have the following two relations. Yeah, you first apply var phi and then phi, we land up back in X, and you actually get an identity, and in the opposite direction. You first apply phi and then var phi, and you should end up back in V. So this gives you isomorphism of two quasi-affine algebraic sets. Now the first case is the most important one. This is localization. This you can also find in the book by Eisenbud, chapter 2, Commutative Algebra with the view towards algebraic geometry. Yeah, so this is a beautiful example, essentially comes from Eisenbud, chapter 2. So localization. So the first thing is you start from a conic. So conic, you have the equation, the polynomial equation. So obviously you have a polynomial, so it's affine, and we will show it as isomorphic to this quasi affine set. So quasi affine set I will write as a1 minus 0. You know a1 is affine, which is defined by the polynomial equation 0 equals to 0, and a1 minus 0 is quasi affine because you are taking the point corresponding to x equals to 0. So yeah, so you're cutting out point 0 via a polynomial. So the second set is quasi affine. So a1 is affine, defined by 0 equals to 0, and you take point 0 out by cutting it with the polynomial x equals to 0. So that's why the right hand side is quasi affine and left hand side is a polynomial, so you can see it is affine. So now let us describe the morphisms between these two. So first I am drawing the conic, and now it is a1 minus 0. So conic is the algebraic set which I will donate by capital X. So conic, which I am donating by capital X to a1 minus 0. So the morphism is given as just the projection. And then morphism in the opposite direction from a1 minus 0 to the conic, which I am writing as capital X. This capital X just denotes the algebraic set xy equals to 1. So write this down for clarity. So the map is what you would have guessed it, x comma 1 by x. This is obviously regular on a1 minus 0, and notice that we have the fractional form 1 by x. Yeah, it's not a polynomial. So now let us generalize the above example. Yeah, you start with the affine algebraic set X. Yeah, this X is subset of some bigger space AN. So X is a affine algebraic set. Now you know from this affine algebraic set you can construct the corresponding ring OX. Yeah, this is the ring of polynomials. Now you pick a polynomial S in it. So then you can construct an open set corresponding to this polynomial S, which we will call as US. So let us see. You have this first set X, like the circle. Then you have OS. You pick a element or a polynomial S in it. Now let us draw S. Now this polynomial S cuts X at 4 points. I'm just circling these points in rust color. Now we'll take these 4 points out of X and we get an open set. So let us draw the open set right under it. So you get an open set, you have 4 points missing in it. So from X you have taken a finite number of points out and you call it US. So you can see why we call it US, because it is precisely determined by the polynomial S and X. So what is this set US? We want to describe this set US. So this US is isomorphic to this set Y. Yeah, this US is isomorphic to this set Y, which is given as x comma t, a tuple x comma t, which is element of x times a1. Yeah, this is a subset of an times a1 because x is a subset of an, such that we have this sx, which is the original polynomial we started with, times this t, which comes from this adjoining a1, is equal to 1. Now this is important. Notice that now we have a polynomial. Yeah. So because an times a1 is an plus 1, so we have a polynomial in an plus 1. We have just adjoined another variable t to it. So suppose you have x1, x2 all the way to xn, now you have adjoined t to it. So you have an plus 1. Now let us show this, that us actually is isomorphic to y. We're just going to copy the above example. You go from us to y, which is equivalent to going from a1 minus 0 to x. You take s, you take x, you go to 1 x times 1 over sx. Obviously you take t as 1 over s, this is x comma t, yeah, so t is 1 over sx, so it just satisfies the equation. Now you go in the opposite direction. Yeah, so xt goes to, just projects to x. Now again y here I am taking as x in the above example, and us is a1 minus 0. Now 1 by sx, you should think of 1 by sx as t. So 1 by sx is nothing but t. So now you see that we have taken this set us and we have made it equivalent to another set called y, which is defined by a polynomial equation in a bigger ring. Yeah, the polynomial equation sx times t is actually in a bigger ring an plus 1. So this is an important result we get. So this standard open set, these standard open sets, you have these standard open sets corresponding to a polynomial. These are isomorphic to an affine algebraic set of the form y, which is just shown above. So this is what leads to localization in Eisenbud's book, and it is a good read to see how it happens. Yeah, it is an affine algebraic set because it is equivalent to the set sx times t equal to 1, and that is why I have marked that, underlined it with green. So you should rewrite this example, basically understand conics and copy it down. So let us recap what we did in previous slide. We start with the affine algebraic set x, then we talk about its ring of regular functions ox, then you pick up a polynomial in ox, and then you form a corresponding open set us, which is a subset of x. So we described this pictorially in the previous slide. Now what is ous? You took up the an corresponding to ox, then you assigned t to it. So yeah, x should be in round brackets rather than square brackets, which is the ring of regular functions, and then you modulo out with the ideal st minus 1, or the equation st equals to 1. Okay, now let us rewrite this. So notice that in general, localization, again you can see this in chapter 2 of Eisenbud's book, that commutative algebra with a view towards algebraic geometry. Yeah, the localization of a ring R with respect to an element S is given like this. Yeah, defined as you adjoin to it another variable t, and then you modulo out st minus 1. Yeah, so the elements of this ring are of the form a divided by s to the power of n, where a is the element of the ring R. and n is any positive integer. So more precisely, you can say that this R1 by S is a subring of the fraction field of the ring R. Both A and B belong to ring R. A belongs to R and B belongs to R, and B is not 0. So now let us compute some examples. Just one more point. If S is 0, then R1 by S is also 0. Yeah, it is just the 0 ring, the trivial ring. Now let us compute some important examples. So the first example is, what is the ring associated with the set A1 minus 0? So we want to talk about this set A1 minus 0. So what is A1 minus 0? You have this entire affine line, and then you cut 0 out with the help of one polynomial. This polynomial is x equals to 0, that is the y-axis. So you cut this point out. So the red point is taken out, and that is how you get A1 minus 0. Yeah, so you can see the polynomial s is nothing but the y-axis in this case. So you have to talk about ring R, then 1 by s, where s is nothing but x in this case, because you're cutting out with x. So you take the original ring OA1, which is the bigger set x, and out of x you have taken 1 point out, and that is how you got A1 minus 0. So OX is OA1, and OA1, the affine line is just kx, and then you adjoin 1 by x to it, and you get a ring of Laurent polynomials. So notice that how set U is formed from set X, and how that is how the entire thing plays out. You need to know what is set X, and then you just divide by the polynomial which essentially creates the open set. So what if you take a affine line and you pick out a finite number of points, say you take out n points. Now obviously all these points have to be defined by one polynomial, and obviously a multiple of x minus a1 times x minus a2 all the way to x minus an is such an equation, yeah, which will vanish at all these points. So now you have to adjoin, yeah, so 1 by s. So the polynomial s in this case is x minus a1, x minus a2 all the way to x minus an, and the ring R is the affine line kx, yeah, because a1 was the original set x from which we took out finite number of points to get u. So the elements of this set look like this. You take a polynomial in kx, and then the denominator is looks like this, where c1, c2, c3, cn, all these are positive integers, that is n, this ci is greater or equal to 0. It's a positive integer. So let us write this down, what I just said. And all these ci's are positive integers. So another example. So you take a plane and take 0 out of the plane. So first we need to describe how this set looks like. So a2 minus 0 is union of two sets. a1 minus 0 times a1 union a1 times a1 minus 0. Now I will pictorially draw these two sets. First set I'm going to call u1, second set u2. So let us pictorially see what these represent. So u1 is nothing but you have the y-axis is missing. Yeah, so you take x-axis, take 1 point out of it, and then times a1. What it looks like is this. So u1 a1 minus 0 times a1 is nothing but this axis. X equals to 0 is missing, and x equals to 0 is nothing but the y-axis. So x equals to 0 is the polynomial which is missing. So keep in mind, now we have to divide by or adjoin 1 by x here. Similarly u2, now you can see by symmetry the x-axis missing, so y is equal to 0. And now you can see when I form the ring of O a1 times a1 minus 0, I will have to adjoin 1 by y to it. Yeah, because y equals to 0 is not in the set here. So what is the ring associated with this? Yeah, so first you start with the bigger set. X was a1 times a1, which is a2. From a2 you removed the y-axis. So you start with the big set a2 and you remove the y-axis out of it. So first we write what was ox. That will be kxy corresponding to the entire set a2. Then you removed y-axis out of it, and therefore you take 1 by x. Yeah, because the y-axis is defined by the polynomial x equals to 0. Similarly, in the second part, you first start with the bigger set. So the bigger set was a2, and from a2 you plucked out the x-axis, and the x-axis is given by y equals to 0. So you adjoin 1 by y to it. So that is the standard technique. But what is OA2? Yeah, OA2 minus 0. Now OA2 minus 0 is equal to OA1 minus 0 times A1 and intersection. Notice we have an intersection here. The union of U1 union U2 becomes OU1 intersection OU2. This is from the laws we had discussed before in terms of how sets behave during rings. So notice the union has become intersection, and when you take intersection of kxy adjoin 1 by x, intersection kxy adjoin 1 by y, you get kxy. So this is what we have. A2 minus 0 is kxy, and this is same as ring of OA2. Okay, so this can be used to show that A2 minus 0 is not affine. Now what does that mean? That means out of A2, if you just take the origin out, that origin cannot be taken out by defining a polynomial. Yeah, because when you take any point out, a finite number of points out, those points have to be defined by polynomials. So we are saying that you cannot choose any kind of polynomial which will just take the origin out and leave everything unchanged, and therefore A2 minus 0 is not affine. It's not cut by a polynomial. So let us see why it is so. So first notice that we have this correspondence. Yeah, so you have x minus 0, y minus 0, which is written by x comma y. This is in one-to-one correspondence with the geometry. That is the points in the space. So the points in the space 0, 0 correspond to ideal x minus 0, y minus 0. So there is a maximal ideal on the left hand side, and on the right hand side there is a point in the plane. So this xy is contained in kxy, which is equal to OA2 minus 0. But 0, 0 is not contained in A2 minus 0. So obviously if A2 minus 0 was affine, we would have it to be an element. So yeah, so for affine we will have to have that one-to-one correspondence. Now we see on the left hand side we get the recover the entire ring, but on the correspondingly to the right hand side we do not have 0 0 contained in A2 minus 0. Yeah, so let me write down where the correspondence breaks. So this is where the correspondence breaks. And that is the end of the story.